this is going to be what I'm going to talking about, emphasizing the point that much of this is work of my students, and as I know, and hopefully as many of you know, having really smart students could be an alternative, a complement, or even an alternative to being smart yourself. So at some points I may, if there's some really good questions, I may have to talk to my students before answering them. So David is my former PhD student, and Omer, who was here last week, is currently carrying the torch on this project and doing really, really complicated things, which I'm just only going to sort of skim over and touch over lightly. But you're welcome to talk to me and also to Omer about this stuff. And also Shachar, who's my former PhD student. Okay, so we can start. No, this technology doesn't work. Okay. Nothing works. Now it's Ronnie might be the page down and page up doesn't work.
Okay, pause. We can continue with the.
No, it's not the connection. It's the PC. Okay. Okay, now hold on. Yeah, page down, page up, love them. Okay. Yeah. Okay, so we can start slowly with stuff we already know. Let's look again over something we've seen quite a few times in the last week and a half. The basic linear mixed model. We can look at it kind of in a graphical perspective. We have this thing from Introduction to Statistics, which is we can think of as just the fixed effects part of our model, where we have a bunch of covariates and some parameters to describe the connection between the covariance and the expected value of y. What we add for the linear mixed model, we can think of it as adding this very large matrix of genetic variance, which say has like 500,000, a million, 3 billion columns, whatever we want to assume. And that also has a vector of parameters, but these parameters are not going to be treated as parameter, but as random variables. So we don't have to estimate them. We can basically integrate them out when doing our analysis, right? And something we typically assume is that these parameters have a multivariate normal distribution. This is like, we can think of this as the infinitesimal model we've been talking about. And I comment that we don't necessarily need to assume it's normal, because the central limit theorem can help us even if we assume it's any other distribution, as long as there are many of them and they have the same distribution. And then the last component we have is what we in statistics would call noise. And this is the same length as the number of observations we have. This could take into account environmental factor, or unaccounted for other factors, and so on. And maybe some random noise as well that is just completely random. And we are going to assume that these errors are IID between them, as we usually do in statistics. So putting all of this together and taking into account that these are now random variables and not parameters in our view, we end up with the formulation we've seen many times of the linear mixed model, right? Saying our vector y has a normal distribution whose mean depends on the fixed effect, and its covariance is basically a combination of the correlated part that comes out of the genetic effect and the uncorrelated part that comes out of the environmental effect. Right? So this is a model, and for our purpose, we're going to just work with this model and not argue with its assumptions right now.
Excuse me.
Yeah.
Could you go back and that's like where is the sigma mu?
Sorry, sigma u. So we see that k is ZZ transpose over m, so sigma squared g is m times sigma square u. Sigma squared g is the overall genetic variance, and this is the variance per this is the variance per SNP. So the overall variance is m times. M is the number of SNPs. Okay, this is an m by n matrix, and this is an n vector. Okay. So also something we've talked about a lot. What are we using these LMMs for? So basically, we use them to do maximum likelihood estimation or restricted maximum likelihood estimation, and develop methods for all the things we want to do with genome-wide studies. So the first thing we want to do is we want to test, right? To test whether or not there's association between each one of the fixed effects and the response, and we may add SNPs to the fixed effects to test them specifically, those SNPs. And what LMM does is it allows us to control for the genetic structure and the genetic correlation through using this kinship matrix K. The other thing we've heard a lot about is heritability estimation, which is basically estimating this variance component of our mixed model, sigma squared G and sigma squared E. Sigma squared G over the sum of sigma squared G and sigma squared E. And another thing that we haven't heard a lot about, but I think it's a very important application, especially in the medical context, is the idea that if you give me some new data, you give me the X and the Z for someone new, I may just want to predict their phenotype, right? So this doesn't pass through the traditional path of discovering associations and then investigating the biology and learning about the disease and so on. We may just want to predict as well as we can, given the data we've had in our genome-wide study. So, and that, if we think about the multivariate normal distribution, I didn't put the formulas here, but they are very nice, then actually estimating this conditional expectation of the new phenotype given our X and Z for the phenotype, our fixed effects, and our genotype for the new sample, and then all our study, that's actually a standard exercise in multivariate normal estimation, right? So this is actually a very nice application of this model for prediction. Okay, so this is very cool and very useful, very widely used, and I think it's a very good model. But so far we've assumed that our phenotype has a normal distribution. In particular, we've assumed that it's a quantitative phenotype. Otherwise, it cannot have a normal distribution. But of course, many of the things, maybe arguably most of the things we're interested in are actually not quantitative, but dichotomous, right? So first and foremost, disease status is something we are most interested in, the genetics of disease. And a disease is you either have the disease or you don't. So what we observe is a dichotomous binary phenotype. And by definition, this binary phenotype cannot have a normal distribution. This we can't, there's no arguing about it, right? And it cannot have variance components that are independent of each other because they have to add up to 0 or 1. So that also means that they cannot be independent of each other. And then there's a common fix to this, which I think is very sensible as well, which is to assume that there is something that is quantitative and normally distributed that we don't observe. And we call that the liability, right? So we assume there's actually a continuous phenotype, which is normally distributed. And because it's unobserved, we can basically assume it has any variance we want to assume. So we typically assume it has variance 1. So this sigma squared G and sigma squared E reduced to just being one parameter. And we say, OK, so let's assume that what we see is a thresholding, is a dichotomization of this continuous phenotype, right? And this is nice because we now have a model that we can work with, assuming normal distributions. Right, so here's an illustration of the liability. This is what is usually described as the liability threshold model. We have a normally distributed liability, and then the affected individuals are the ones with the biggest liability. And because actually this is a disease that is not common, even common disease is not common in terms of being 20 or 30%. So this may be a disease with about 1% prevalence. So that means that there's actually a small tail of the distribution of the people who are affected, right? Because it's just 1% of the population. So this is the picture we often imagine, but actually our model, our standard LMM, gives a picture that looks more like this, right? Because we said that the mean actually depends on the fixed effects, and then the phenotype is normally distributed around the mean, right? So actually the marginal distribution of the phenotype, which in our case it's this liability, is actually not normal, but it's a mixture of normals. Right? And how complicated is the mixture actually depends on how many fixed effects we have. So if we have just one fixed effect that has two possible levels, so X is one-dimensional and has just 0, 1 possible levels, then that would basically mean that our liability is a mixture of two normals. Right? And we can still say that the tail of high liability is the individuals who are affected. That's not a big problem for us, because remember, our fixed effects are estimated separately, and really all we need is that given the fixed effects, we have a normal distribution, and this still holds in this model. Okay, so we have the LTM, the liability threshold model. And one thing we can think about is how does the distribution of y now depend on the thing that is normally distributed, right? And in particular, how does it depend on our explanatory variable, which are the x's and the genotype z? So we can start by thinking about something that hopefully most of us has learned, which is generalized linear models, and say, now let's for a moment assume that the b are also parameters and not random variables, the effect sizes of all the SNPs. In that case, we can say that the probability of y to be 1 given x and z is the probability that L falls in this small tail, right, where we have a high variance. And we can easily see that this is something that depends on this cumulative normal distribution. Phi is the cumulative standard normal distribution. So we can easily convince ourselves that given the phenotypes and the genotype and the fixed and the explanatory variables x, the thing that we still don't know is the size of the error, epsilon, right? We said that epsilon has variance sigma square e. So basically, this is the probability to fall in the tail given these values. Okay? T is the threshold, the liability threshold. But this is not. So this is nice, because if we only had these fixed effects, then we would know exactly what to do. This is basically a probit regression. This is a generalized linear model. So it's not a logistic regression that you were used to thinking about, but it's something that is actually similar to logistic regression and also belongs to this family of generalized linear models. So then we would know exactly what to do. But actually, in our case, remember that our b's are random effects, so they are random variables that we want to basically integrate over in doing our estimation. So now we can write this also in a way that's that you don't immediately see the similarity, but it's the analogous way in the case that these b's are random variables. So if they are random variables, again, we have the same, exactly the same formulation as we had before for our liability. Now it's not the phenotype, but the liability that has this multivariate normal distribution. And our phenotype is just the indicator of being bigger than the threshold. So we've really done nothing here. But the representation we really want to think about is this representation, which is equivalent, but we want to spend some time making sure we understand it. So now let's define this vector G of genetic effects. Okay, so G is basically Z times B. It's the genotype times the effect of each SNP. And because the effects of the SNPs are random variables, then actually this G is just the component of the random effect that has this correlation matrix K. Okay, so G is just the genetic random effect of each individual. It's a vector of size n of the genetic random effects of each individual. And now we can write an equation that looks a lot like the fixed effects equation, which says that the probability to be 1, if you tell me x and now you tell me G, right? So that integrates your Z and your B, or your Z and the overall B. If you tell me those, then I'm back to something that looks exactly like the fixed effect model. Notice that sigma E that's a different way of writing sigma E, because we assumed sigma square G plus sigma square E equal 1. Okay, so here we see that given this G, if you tell me the value of G, I'm back to something that looks exactly like the equation on top. Right? But I have to take into account that now this G is a random variable with this covariance matrix that I have here. Okay? So, so this is my setting, and this is actually this or this, whatever formulation we want. That's a way of saying that now we don't have a generalized linear model like logistic regression. We have a generalized linear mixed model, because it has random effects and fixed effects, and it has this thing that is normally distributed, and then something that we can think of as a link function. This is usually what's referred to as the link function. Okay, so So what can we do? So basically, we have a well-specified model, and we want to carry on our tasks of testing, heritability estimation, prediction within this model we've defined. Okay? And one thing that is often done in practice, that goes back to our initial discussion, is just to take this 0-1 phenotype and apply regular linear mixed model to it. And do testing with it, do heritability estimation with it, do prediction with it. And then we have some sort of things that we can do after applying the LMM, such as this Dempster-Lerner transformation that I'm not going to go into, that we can apply to the results of just doing an LMM, which assumes normality on the 0-1 data, which is not normal, okay? And the one thing that we can say is that in the setup we've described so far, the proof by simulation seems to work pretty well for this methodology. But if we take a step back and be more careful, then we have to say that this conceptually, we cannot start from applying a maximum likelihood normal method to 0-1 data. So, so we're doing something that's hard to accept even if it works on our examples. But we are now in a setting called GLMM that actually there's a lot of literature and a lot of methods that do allow us to solve this GLMM problem as we posed it. So do maximum likelihood or the analogous of a restricted maximum likelihood for the problem, for the probabilistic setup we've posed. So now I'm going to spend a few minutes sort of describing the approaches to solving GLMMs and talking about basically why it's a good idea and why it may not be such a good idea to take the GLMM approaches and solve our problem as posed. Okay, so this is basically, we want the likelihood of our parameters, right? Our parameters that we want to estimate are the fixed effects and the variance components, and we have just one variance component because we assume they sum to 1. And we can think of it as integrating over this probability of the vector g given the phenotypes, and then multiplying it by the probability given the genotypes, and then g doesn't depend on x, right? G just depends on or the covariance of g depends on the genotypes, and g doesn't depend on x in any way. And then we don't only want the density of g, we actually want the phenotype to be correct, right? If we observe 1s, we have to integrate over only the cases that y equal 1. Where we observe 0, we have to integrate. So basically, this is like saying we want to integrate over a corner of our multidimensional space, right? We have an n-dimensional space. So the thing we want to integrate over is distribution of g. We have an n-dimensional space for this g vector, and we need a corner of this space to integrate over. Why a corner? Because the observed y tells us that we are in one corner of this multidimensional space where some of the coordinates are 1 and some of the so some of the coordinates are above the liability threshold level and some are below, right? So this is like a quotient of our space, but it's a quotient of an n-dimensional space. It's a corner of an n-dimensional space. So this is the integral we want to do, and this, I don't know if it looks daunting, but it's actually a very difficult problem. So just directly integrating this, directly and accurately integrating this, there's no known methods for doing that. Because, so basically the things we know how to integrate are Gaussians. And this we have a Gaussian distribution here, but we're actually interested in a truncated Gaussian distribution. So we have a big multidimensional Gaussian distribution, and we're truncating it to a corner of the space, of the n-dimensional space. And that integration we don't know how to do directly. But there's very nice ways for doing approximate computations on this. And I'm very quickly going to go over the type of approximate computations for GLMM that we have. So one obvious thing to do, like any integration problem, is try to do sampling, important sampling MCMC. And that turns out to be theoretically or in principle attractive, but in practice it doesn't work because in sufficiently high dimension it just doesn't converge quickly enough. So in theory it's a good idea, and we can say basically how accurate our approximations are, which is a big advantage, but we don't get we usually don't get good methods, competitive computational methods from doing MCMC. but it's certainly an alternative.
Why? Because the guarantees are not enough. The theoretical guarantees.
Yeah, they're just guarantees. What you can say is if you run it long enough, you're going to get accurate estimations. But this long enough is too long for practical purposes.
Actually, both of them depend on how you define the importance sample.
Right. Right. So really, MCMC, I view it as a way of doing importance sampling because I can't directly do importance sampling in most cases. I don't think that in this case we can directly do importance sampling. But the thing that I want to give a little detail on is this idea of analytical likelihood approximations. And I'm going to give you some details about these two methods in a little while. Pairwise likelihood is actually a very important method that I'm not going to be talking about. And then we have the Bayesian approach, which, I mean, saying I want to be Bayesian is just saying that I want to do a slightly different integration than the integration I wrote here, but I still have the difficulty of integrating if I want to be Bayesian. So I'm going to give you a little detail on the Laplace and EP approaches because I think they are very elegant. They have some ideas that are really interesting. And so Laplace approximation for GLMM is kind of something that statisticians have been doing for a long time. And EP is really an approach that came out of machine learning. And it's this is the seminal book on Gaussian processes. And Gaussian process classification is really just a different formulation of the same GLMM that we've written. So some of you may have heard of Gaussian processes. There's a close analogy between Gaussian processes and linear or generalized linear mixed models. Okay, so what's the idea here? The idea is that if I want to integrate easily, basically the only thing I know how to integrate is Gaussians. And I can also integrate scaled Gaussians in the sense that if I take something that's a Gaussian and I scale it, now I don't have a distribution anymore, I have some function. But basically, all I need to do to know the integral is to figure out how I need to scale it down to get back to a Gaussian distribution, and that's 1 over the integral of this function, right? So our goal is going to be to estimate the function. So the functions we want to integrate, this function we're trying to integrate here. This function, it's not a distribution because then the integral would be exactly 1. But we're going to try to estimate this function with a Gaussian, with a scaled Gaussian, to get as close as possible with a scaled Gaussian. Then we know the integral, it's 1 over the scaling factor to get a Gaussian distribution. Okay, so this is actually the common idea to both of these approaches.
So you try to approximate your function by a Gaussian.
Yes.
With just what are the parameters? So what you try.
Yes.
So the approximation is, or quality is just the parameter because Gaussian is Gaussian. Just what are the good parameters or what?
Exactly, and it's two different ways of getting, basically EP and Laplace is two different ways of getting a scaled Gaussian approximation to my function I want to integrate, right? There's a lot of details and they're quite complicated, but that's the only general idea. And the difference between them is how they do the approximation. We can think of Laplace as finding the mode, the top of our, the thing we want to integrate over, the function we want to integrate in, and then estimating a scaled Gaussian around this top point. So we're committing to the mode and then doing the best Gaussian approximation around this mode. Whereas EP is under some decomposition that I'm not going to be talking about. Under some strong assumptions, we're still going to find the best possible approximation using KL measures of different types. So without going into details, let me just show you how it looks visually. So that's kind of a reasonable visual approximation of what we do. We have this thing we want to estimate, this yellow area. So Laplace would be something like finding the mode and then doing the best Gaussian approximation around the mode. And EP would be something like just finding in general a Gaussian that is as similar as possible using the appropriate measures to, yeah.
For calculating liabilities, p-values and so on, usually you're interested in scale areas.
Yes.
So are there extensions where you like exponential twisting or something like that to explicitly model the tail as opposed to the pole? It's
a good question, not that I know of. So one thing that immediately comes out of what you're saying is, for example, the coordinates where we observe y equal 1, what's the most likely point in those coordinates? It's actually right on the boundary, right? Because the liability has this normal distribution. So the point that's right on the boundary is the highest point. As you move away from the boundary, your distribution dies down quickly. So you're trying to estimate something that's like a 0, then big, with a Gaussian, right? But that's just in one dimension, and we actually have n dimensions with correlations. It's very difficult, at least for me, to imagine what this thing is doing. In practice, the Laplace approximation is, as far as I know, always inferior to the EP approximation. So really, but it's much faster. So again, we have the usual trade-off. Okay, here's a maybe slightly more informative visualization. Now we are in 2 dimensions. We're trying to estimate this function. So Laplace would find so now we're thinking of 2-dimensional contours, right? And this is like the highest point of the distribution of the function. So Laplace would first center on this highest point and then do the best Gaussian approximation around that. And EP would try to locate a Gaussian that looks similar in a more general sense. Okay, so to summarize what we've talked about so far is what's often practiced, which is just do LMM, is not justified, but of course it's very efficient and it seems to give reasonable results as far as I know. So we can argue whether or not it's the right thing to do, but we can solve the GLMM problem and get, for example, get estimates and get predictions using the GLMM approach. It's very hard to design tests when all you have is approximations. Right, so that's kind of a bigger problem to do statistical testing based on approximations rather than exact solutions.
What do you mean by that?
Well, so the null distribution is no longer a null distribution if all you have is an approximation of the, is no longer a valid null distribution. If all you have is approximations, and if you're doing EP or Laplace, you don't really know how good your approximations are. So, I mean, there are issues that still need to be solved. But we really haven't talked about the biggest issue yet, which is, so how long do I have? When did we start? Do you know?
You have at least.
Okay. So really, we haven't mentioned the words case control sampling yet at all. And this is where it really gets interesting. Yeah?
The biggest part, empirically, what's the experience applying these different methods and comparing it to just assuming it's normal?
Yeah, so I don't have that much experience, and one reason is that really no one does what we've talked about so far. What everyone has is case control data, right? So really this question should be asked again after the next part of the talk. But it's very hard, because everything is very hard and it's going to get much harder now. It's very difficult to figure out what people actually did and to sort of repeat the experiments and get the same results. It gets very, very murky. So I actually don't know the answer to what you're asking, even for the case control. I can demonstrate, as I'll show you, that some of the used methods are invalid. But others that are claimed to be empirically valid based on simulations, I don't know what to say about that. And they may be the best thing to use in practice. Okay, so
Actually, so what
yeah.
we found was that, we actually are part of the people that led people in the wrong direction by just setting things to 0 and 1. But what we found is that when you're just looking at one snip at a time, it actually works fine. But I think what Noah found is when you add like covariates and things like that, that's when everything falls off the rails.
right, but you're talking about case control, right?
Or case control.
Which we haven't really talked about yet at all. I think for the unascertained case, I think it would actually carry through for having covariates as well. I suspect, I don't know. But let's talk about the case control case. So really, when we're doing disease studies or really almost any binary phenotype, we're not doing random sampling, natural sampling. We're doing case control sampling, meaning we're upsampling the cases in the study relative to the prevalence in the population, right? And this is really a huge deal from a statistical perspective, because we can no longer assume our regular GLMM, which basically only asks what's the distribution of y given our explanatory variables. and I'll show you why. And I also argue that at least for some of these things, trying to apply LMM no longer gives results, valid results even in simulation. So by violating more assumptions, additionally to only having normal versus 0, 1 data, we've gone to a situation where we can no longer apply LMM and hope to get good results. And also, unfortunately, I'm going to argue that the computational approximations we've discussed don't apply anymore to this setting. So we may be completely lost about what we should be doing. I'll offer some solutions to that. Okay, so let's first of all understand what the problem is. So we have committed, one very important point to understand, that we've committed to this liability threshold model, right? Which is an assumption. It's not a fact. But we're going to go, but this assumption, I think, makes sense, for example, because of the central limit theorem. So assuming that what we see is an accumulation of small effects, sort of very naturally leads us to assuming this normal distribution, right? At the population level, which is our stated LTM. Now what happens when we assume the LTM at the population level and we do case control sampling? That means we've taken this tiny tail here and upsampled it extensively, right? So if we now look at the liability distribution of a case control sample, it doesn't look like a nice mixture of Gaussians. It looks like a nice mixture of Gaussians with this heavily inflated tail, right? Which is very, very, very far from being a mixture of Gaussians. Okay? So if we are assuming the LTM, then this no longer has anything that's like a Gaussian distribution. Well, we've upsampled the cases. We assumed in the population the LTM, and we now have 50% cases and 50% control. So the way I like to think about it is think about taking our population before we do our sampling and creating a new population out of this population, which contains all the cases and the random sample of the controls. And now we're going to sample from that population. Okay, so in that population, what's the distribution of the liability? This is the distribution of the liability in that population.
So it violates the
Well, it's very far from normal. So if we do something and assume that this is normal, we're going to be in trouble. So let's look at some of the consequences of this. So one very interesting and maybe counterintuitive consequence of this is if we assume the genetic and the environmental effect are independent in the population, they are not independent in our case control population. Okay, and we can see it visually very nicely. So this is the liability threshold, and now we see a two-dimensional distribution of genetic and environmental effect. This is just, we think about the individuals one at a time, right? We don't worry about genetic correlation. We just think about the individuals one at a time, and each individual is a point here. If we were in the LTM, then we would have a cloud and we would have independence between genetic and environmental effects. Now, because we concentrate people around this liability threshold, so we pushed a whole bunch of people to the same side of the distribution, and in this case, we get empirical distribution of 0.53. So any method that assumes independence between genetic and environmental effects is by definition assuming something wrong. Okay? The other thing we now have to worry about is what does the effect of the SNPs look like? It was normal in the original distribution, and we can easily do some math and see that actually these Bs are no longer normal as well. They now have these, in the extreme cases that the prevalence is low and we do a 50-50 sample, they have this bimodal distribution. And the liability distribution, this is actually what we've seen, that the liability is not normal. But this has actually major effect if we look at it from the other side. So let's ignore this phenomenon, and let's assume that the liability in the case control sample is normal and apply a method that assumes this normality. Then now we can ask ourselves, what are we assuming about the liability in the population if we assume normality in the case control population? And then we get these kind of pictures, that we're assuming the liability behaves like a nice normal, and then it drops almost to zero immediately because we invert this inflation. Okay? So if we think that this is a reasonable distribution for the liability in the population, we may say this is fine. But we have to understand that this is what we're assuming on the behavior of the liability in the population. So at least as long as we want to assume LTM in the population and not in the case control population, we have to be very careful about how we do GLMMs in case control studies. Okay, so one thing that comes out of this, if we want to be careful, is we can say, as I'll show you, the likelihood approach is just too difficult. So let's not try to do likelihood-based solutions. Let's try to find something that we can say explicitly what it does, and we can calculate reasonable estimators with it. Right? So this is something we've been doing in my group for a while. And we basically have published solutions for two modes of this problem. One for phenotype prediction, David's work in 2014. And it basically says if what we want to do is prediction, then we can actually use a likelihood-based solution, assuming we know the heritability. So we don't have a good estimate for the heritability, but if we estimate the random effects or the variance components, we can actually, so this conditional, what I talked about, the conditional expectations for multivariate normals are actually carry through nicely to this case. This is some observation that other groups have used as well. Well, it's assuming, yes, that's where heritability is defined. Otherwise, I wouldn't call it heritability, just variance. And then we have another paper which deals with heritability estimation. So actually, we could use this to do this. And I'm going to tell you a few words about our heritability estimation approach. So basically, what we're going to be using is we can think of a method of moments instead of a maximum likelihood approach. So basically, we're saying, let's see if we can figure out what's the distribution for both of the phenotypes to be 1, conditional on their genetic correlation. Let's see if we can estimate that under ascertainment, given the heritability. Okay, if I'm told the heritability, I want to find a parametric connection between this probability and the genetic correlation between the two individuals. This is just one cell in the K matrix, right? Our K matrix is all pairwise correlations between individuals. And by common sense, we expect that if the heritability is high, it means that people who are similar genetically are also going to be similar in the phenotype, right? So it's clear that this has information about the heritability. We can think of the slope of the regression of the phenotype correlation on the genotype correlation, or the phenotype relationship on the genotype correlation. So what we want is a formula of this form, that this probability is some function of the heritability times the genetic correlation. And we probably can't hope for this to be truly linear, so we just want to have a small residual. And why is this a reasonable way to do it? Because we generally assume in GWAS that the pairwise correlations are small, so we may hope that what we're neglecting here is actually a small residual, right? Because the RIJs between unrelated individuals are all typically very small. Yeah?
Okay, so this is requested. What is not requested? So I see the big O over RIJ, but what you say, this I don't like. This I don't want. Like big O, like
well, no, if I have if I have this representation, then I have a way of estimating sigma squared g by inverting the function f. That's all I'm saying. Doing a regression and then inverting the function f, right? So we regress the phenotype products on the RJs, and then we apply f inverse to the slope, right? And this can be thought of as an instance of this well-known method called Huysman-Elston regression. But really, the nature of the function f is kind of unique to that has to take into account the case control sampling. Okay, so if the RJs are small, then this will be a reasonable approximation, say almost unbiased estimate of the sigma square, and almost unbiased because the inversion is not linear and because we are neglecting this squared term. By the way, if RIJs are not small, we can, and we do in the paper, also calculate the square term here. So then we can invert a much more complex function of the heritability. Okay. This actually very well-known formula is what comes out when there are no fixed effects. And when there are fixed effects, or we need the second order term, it actually gets much more complicated. So this formula contains in it the proportion of cases in the population. K is the proportion of cases. This is the proportion of cases in the study. So it's, let's say, 50% typically. This is the proportion of cases in the population, K. So this is like 1 in 1,000. And this is the function, meaning to invert it, this is actually turns out to be a linear function of this argument. So we just put this to the other side and apply it to the slope of the regression. OK. Sorry? T is the liability threshold, and this is the Gaussian density at the liability threshold. And with no fixed effect, we just have a single Gaussian, right? With fixed effect, it gets much more complicated, and with the second order term and so on. But, I mean, we could discuss this formula, but intuitively, it's clear on what things it depends. Depends on how we sample, and it depends on the prevalence in the population through both of these values, right? This is the integral, and this is the density. OK. So now we get, maybe for the first time, to see some results. And the idea is this. Let's simulate. And this is the true heritability. This is the estimated heritability. And basically, this is where we want to be. And our PCGC estimate in this case are all on the line. And this is the first time I'm actually introducing a different method, which is probably the most widely used method. That's the Lee et al. Method for estimating heritability in case control studies. And what they do is they apply LMM directly to this 0-1 case control data, and then they have a correction to the resulting heritability or variance estimate on the original scale. Okay, and their correction actually has the same algebraic form as the correction I just showed you. But it gives incorrect results. Okay, and so just as a fact, and these results have since been repeated, our results, that this gives incorrect results. And one may ask whether it is because they are applying not the right correction to the results of LMM. Maybe there's a different correction. I don't know the answer to that, but I think there cannot be a correction that would consistently give correct results when applied. When applying LMM to case control GWAS, assuming the LTM, because that, as far as I understand, there's no way this kind of approach could work. This just demonstrates that as we increase the sample size with the other parameters remaining the same, actually this LMM-based approach is not the bias that it gives in estimation is not consistent. It's actually the bias is increasing. The estimate is decreasing as the sample size increases. Okay, so we could discuss what's wrong with it, but to me the fundamental thing that's wrong with it is we don't go and apply LMM to case control 0-1 data, and then try to correct what we've done. Okay, so a few more minutes, Elazar, is okay? Okay, so I'll go quickly over this. So really, these papers of David are representatives of an approach that says, let's find something we can do reasonably well and apply that to this case control data. What I'm going to be talking about now is the attempt to be more ambitious and do proper likelihood modeling and inference in this case control linear mixed model, or GLMM. Okay, so really I'm going to be talking about the challenges and not much about the solutions, because they are really very complicated. But why is it difficult? So I think we've touched already, but the standard GLMM framework does not apply anymore when we have the case control setting. So for example, the fact that the sampling depends on the phenotype means that the kind of likelihoods we are used to thinking about in this community, which are prospective likelihoods, the probability of the phenotype given the X's and the Z's. That's actually not a correct likelihood to think about, because our sampling dependent on the phenotype, right? So the right likelihood of our data, the correct likelihood, really the prospective likelihood we are used to is a reduction from the full likelihood that we can prove is a good idea in the cases we're used to without the case control sampling. The reduction from the full likelihood, which is the joint likelihood of Y, X, and Z, to the conditional likelihood of Y given X and Z, is we can prove that it gives basically what we want. It's equivalent in terms of the parameters we're interested in. Under case control sampling, this is no longer the case. So it's no longer easily the case. So we need to consider the retrospective or full likelihood if we really want to be rigorous. And that immediately leads us to problems that are unsolvable, that require us to model the marginal distribution of our explanatory variables and of the genotypes, and it's just impossible. But if we very carefully read the statistic literature, we do conclude that we can do something like the prospective modeling we are used to. That's no longer a proper likelihood solution, but it's almost as efficient as the likelihood solution. But it's not just ignoring the ascertainment. It requires us to change our, basically to change the GLMM Lig functions. I won't go into that. But we can reformulate things in a way that would be almost maximum likelihood. But then we are asking ourselves, can we solve these problems that we've posed? And that leads us to the computational challenge, which is the standard GLMM approximations like EP do not apply anymore once we basically change our link functions to take into account the ascertainment. MCMC can still be formulated, but it does not seem to converge at all when we've tried it. And the most interesting point is that the EP formulations of GLMM does not apply anymore. And one of the main things that Omer has done is sort of invent a new EP-like algorithm that does work on the on sort of the modified problem. And there's additional approximations that I've not discussed that can be adapted. In particular, the pairwise likelihood one is very interesting because that's a sort of a likelihood-based approach that's actually very similar to what I talked about for PCGC. Okay, so finally, I want to show you some results based on very, very complicated software and waiting a long time for the results. So there's no guarantee that it's accurate, but it's what we have so far. So this is trying 3 different approaches, in this case for estimating irritability in simulation. And this is the accuracy. And here we have some measure of robustness. So if we misspecify the covariance, do we still get reasonable estimates, which is actually an important question for GLMM. I mean, we can concentrate on these areas for our purpose, without covariance misspecification. And we see that the 3 methods we implemented, which are the modified EP, the pairwise maximum likelihood that I haven't talked about, and this moment-based estimator, generally behave similarly in terms of the error. It seems like the EP may be the most accurate, but it's not clear. Okay? But in simulations, they seem to work quite similarly as long as the covariance is well specified. When it's not well specified, we see that the pairwise method suffers a lot more than the other methods. And then we can go and apply to real data and say, do we get a picture? This implies that when we apply the methods to real data, we should get similar results between them, maybe. Or this applies that if the data doesn't comply with our assumptions, then we may get pretty similar results from these two and then different results from this one. And this is actually what we get when we apply it to real data. Just 1 second. This is applying it to phenotypes from the Wellcome Trust Case Control Consortium. And we see that these 2 methods actually give pretty similar heritability estimates, and the pairwise method gives much lower estimates. So we may try to hypothesize that these consistent estimates may be okay, but I don't know. These are the yellow ones are the published PCGC results from the literature.
What's the PML again?
PML is pairwise maximum likelihood. So it's actually replacing your likelihood with, so your likelihood is like a product over all observations. You do a sum of all the pairwise observations. So it's actually very similar in spirit to what PCGC does. And we don't know why it gives very different results. It's still complicated. We don't know why it gives different results. Question?
Yeah, how is defined a percent pairwise covariance specification?
I don't remember. It's a good question. I don't remember. Finishing. OK, so summary. That's a good time for summary. I hope I convinced you. I convinced myself by sweating here that it's a hard problem to apply these GLMM approaches to case control. And that we should not go about starting from applying regular LMM to case control studies. We have some practical solutions, debatable, but at least we can say exactly what they do for heritability estimation and prediction. And we've made progress on doing likelihood-based solutions. This is the last part I talked about, but it's still, it's far from being applicable for large data, and it may never be applicable for really large data. I haven't talked almost at all about association testing in the context of case control. There's some work even that's been done in this room, some partial solutions, but I didn't have time to discuss that. Thank you.